Ah, there you go.
Yes?
Yep.
Okay, wonderful. Hello. Uh, my name is Jonas. I am currently a PhD in Münster, and I will talk to you guys a bit about my master thesis, which was written in Lean. And I hope to maybe shine a bit of light on the experience of a relative beginner proving stuff in Lean. Um, my talk consists of roughly two different parts. I will talk a bit about condensed mathematics and then my experience with non-trivial Lean. Um, so first, the basics, some light condensed mathematics. For those of you who are not familiar with condensed mathematics, this is a theory created by Dustin Clausen and Peter Schulze to sort of capture behavior of mostly topological abelian groups and variants of them. And one of the main reasons they're interesting is because they're not nice, where nice has very specific examples. For example, if you look at the real numbers, then they form what's called a topological abelian group. This is a group which is also a topological space. And somehow we can give the real numbers two different topologies, for example, the normal Euclidean one and the discrete topology. And we have a morphism of topological abelian groups from one to the other. This is a very simple map. It sends every real number to itself, and somehow this is injective and surjective, but it's not an isomorphism as you would expect from abelian groups. And this is because the inverse is not continuous. And so the goal of this condensed mathematics is to somehow fix this issue with topological abelian groups and topological vector spaces. So I assume that many people here will be aware of some of the condensed mathematics that's been done in Lean. Quite a while ago at this point, a challenge was set by Peter Schulze to formalize a theorem about liquid vector spaces. This turned into the liquid tensor experiment, which successfully formalized some very complicated mathematics. Um, this was written in Lean 3, which by now is 3 years old. And the project might be older, I'm not sure. And so recently, a paper was published, Categorical Foundations of Formalized Condensed Mathematics, which aimed to sort of redo some of this work and make it available in MATLib. And so this is somehow the modern approach to condensed mathematics, which was nice because it meant that I didn't have to use Lean 3. Um, Let me give some very quick information about how this is supposed to work. So light condensed mathematics, like I'm sorry for this slide, it's terribly full. Light condensed mathematics is built on light profinite sets. These are profinite sets which are second countable. They're pretty small. And you give this a Grothendieck topology generated by sheaves of finite collections of jointly surjective maps. This creates a site, and this site is much nicer to work with because the category of light profinite sets is essentially small, meaning that we can do a bunch of stuff without having to raise universe levels. Um, in condensed mathematics, we then look at sheaves on this site. And so a condensed set, as you can see on the right, is a sheaf on this site, and this sheaf is a sheaf of types or a sheaf of sets. For this talk, it will be a sheaf of types. Um, and a condensed abelian group is then a sheaf of abelian groups. And there are a bunch of functors. One can think of a light profinite set as a condensed set. In fact, these condensed sets are supposed to generalize topological spaces. And in the same way, you can turn a set into a free abelian group. You can turn a condensed set into a free condensed abelian group, which is supposed to be some topological space. But of course, it's really a sheaf in some category. Um, Now, one of the sort of interesting objects in this category is called is the sequence space. And I won't actually define the sequence space here, but I'll define something closely related. So you can take the natural numbers and give them the discrete topology. This is a very simple topological space. But once you take its one-point compactification, this is some mathematical tool to turn a topological space into a compact space, it becomes a Lie profinite space, a Lie profinite set. And it's a very interesting one because it describes convergence behavior of sequences. And if you're using the functors defined earlier, you can turn this into a condensed abelian group. And in the light setting, so for light condensed abelian groups, this object turns out to be internally projective. And this has many nice corollaries and applications in the theory of solid condensed mathematics, which is supposed to be this generalization of non-Archimedean geometry. And so what I've done for my thesis, as the title of this talk hinted at, is I've proven that this object is internally projective. I've written the statement of the theorem at least. The proof is a bit longer than is allowed than I can fit on one slide, unfortunately. But I would like to give a quick sketch of this proof, if only to then afterwards be able to tell you that which parts were easy and which parts were hard, and which parts were hard because I made them hard. This object is internally projective if for any diagram below with the maps from X to Y and epimorphism, we can find some cover, some surjective map from an S prime to S, such that we get a commutative diagram of this shape. This is not immediately the original definition you might think of, but if you try to write things out, you get to this, and this is a much more concrete statement than something being internally projective. And so this is sort of the goal my thesis worked towards, and with some help, with a lot of help from Dagur Asgarsson, who was mentioned very quickly. He's in the MathLib initiative team. You can turn this into a proof that this object is internally projective. If you want to prove this, somehow the first step is, well, you have this input, and your first step is to produce this topological space S prime. And then afterwards, somehow you need to construct this lift. And so these two steps are sort of the two steps in which I separated my proof. There's somehow a lot of manipulation of topological spaces. So we start with an epimorphism, and you take a pullback, and then you create a product with this covering space, which is somehow a pullback of fibers of it's a very technical proof with a lot of manipulation of somehow all of these objects which occur. Um, and in fact, that's actually what makes it such a great candidate for formalization, because my computer will do all the difficult stuff for me, which is remember everything that I need to do. Um, and so once you've done this second step, you can do all this algebraic manipulation afterwards, which means that somehow uh, you get this somehow the proof is split up into two very nice separate things, which means that this proof doesn't only work for abelian groups, but also for arbitrary modules over any ring. Um, and I mean that's all I'll say about this proof. It's I think it's 2 or 3 long lean files, but it's not really the point of what I'm going to talk about. Instead, what I'd really like to talk about is something different, which is the experience of someone with not a lot of experience writing writing non-trivial code in Lean, somehow formalizing difficult theorems. Um, and so I do have some prior experience. At some point, I decided that I wanted a bachelor's degree in computer science, which I guess helps quite a lot. I like functional programming, which means that somehow the concepts of Lean translated very naturally to things I already knew. I attended the machine check mathematics workshop in Leiden, I think 3 years ago. I don't remember. Where of course, somehow you learn the basics, but after that, you're on your own. So I have some basic experience, but I'd never really formalized anything larger than some basic definitions or easy proofs. Um, and so I think the main topic that I would like to talk about is the gap between a proof and a nice proof. Um, Now, formalizing a proof can be easy. I say can, of course, there are many very difficult proofs, which are also difficult to do in Lean, but some proofs uh, can be formalized in a straightforward manner. But what I've experienced, and what I'm sure most people in this call have experienced, is that formalizing a proof well takes much more effort. Um, Somehow this is an entirely different skill than maybe doing pen and paper mathematics, and it's somewhere in between software engineering and mathematics. And I'd like to give you an example of this. I will give you a theorem or a lemma, which is lifted straight from my master thesis, and I will give 2 different proofs. They're nearly the same proof. The basic idea is the same, and one is significantly harder to write down in Lean than the other for a whole multitude of different reasons, which we'll see in a bit. So first, so if we have a category with a subcanonical Grothendieck topology, such that all sheaves on that site preserve finite products, then the sheaf Yoneda embedding preserves preserves finite coproducts. Now, there's a proof that I wrote down on the blackboard of my supervisor to convince him that this is true. It took me 1 minute, and he was convinced, and he said, "Yeah, that's true." Um, so by the Yoneda lemma, we have this natural isomorphism. And so the I've written underlined for the Yoneda embedding, which I guess comes from the contents mathematics notation. Somehow there is this natural isomorphism between the co-product of the Yoneda embedding and the Yoneda embedding of the co-product. And this is the natural map that is defined by the universal property of the co-product. And this map is an isomorphism, and so both of this functor preserves finite coproducts. Now another proof, which is slightly more wordy, is instead of showing that our cone is a co-cone, we show the opposite cone is a limit cone. Then the co-Yoneda functor jointly reflects limit cones. So we can apply the Yoneda functor and see if we still get limit cones. Then, because we're jointly reflecting limits, we need to check for every object of our category. But we can do that because by the Yoneda lemma, it suffices to show that X preserves the limit, which is exactly the input that our theorem had. And so the theorem is true. Well, let's see these two different proofs. I've put them both on the next slide. The one on the left is mostly there for comedic effect. Somehow this proof on the left is ugly, it's horrific, it's complicated, and what happens there is somehow a proof which works very well on pen and paper somehow doesn't translate to lean. And this proof on the right is somehow much more elegant. It works much more generally. It doesn't talk about coproducts at all. Somehow it only talks about limits of a certain shape which are preserved. It doesn't care about coproducts. And this thing on the left somehow works only in this very specific context. There's many reasons for that. One of the major red flags, which I should have immediately realized when I started writing this proof, was the proof on the left uses this lemma called preserves coproduct of isocomparison. It's very useful. It says that a functor preserves coproducts if this comparison map I mentioned earlier is an isomorphism. And this is, I mean, it's a nice lemma in theory, except the fact that there's no API like it for similar limits maybe means that this is not the right thing to use in this context, because this is supposed to be a theorem that works in a more general context. Somehow that's a red flag that I should have seen. There's also a bunch of size issues. It's very well handled on the left. There's only a simple U-lift functor somewhere, and that's it. And on the left, these universes cause a lot more headache. Somehow, what you can't see is that there is a composition of that there is category theory composition and regular function composition mixed through each other, because somehow there are objects living in different universes and we need to be able to talk about them. And it's just, I mean, it's just a painful proof. This now this I need to give credit here. This proof on the left was written by me. This proof on the right was not written by me, it was written by Dagur, who somehow managed to turn this ugly piece of code on the left into this beautiful short proof on the right. And that brings me to the main point of my talk, which is how do I go from writing this thing on the left to this thing on the right, except just doing it a whole bunch? Somehow I am, as a beginner, able to write compiling proofs for the most part. Of course, not always. And I would like to go to writing nice proofs that don't get 10 different comments when I try to open a pull request. Um, and of course, I can just, a main part of this is practice, of course. Everyone who writes very nice lean code has done it 1,000 times more than I have. Um, and the main question I'm asking is there a faster way to get there somehow? Um, I think personally, the best way to learn any skill is to get feedback. Uh, and the way that I learned most about lean was at some point Dagur visited Amsterdam and sat next to me for what I'm sure was one of the most frustrating afternoons of his life and helped me program parts of the more complicated uh, stuff of my proof in lean. Um, Another thing that really helps, I think, is somehow this extensive knowledge of MATLib. Uh, what I did for my thesis is I needed this explicit description of pullbacks of certain topological spaces. And so I went about writing it. I did all of it and it worked. I used them in my proof. And then I got a comment, a message that saying, you know, I already did all of this work, right? It's in MATLib. Um, uh, and so somehow I had missed that there was this file doing exactly what I'd done. And it was just, well, a bit, uh, I'm not sure. It wasn't a bit demoralizing, I suppose. Um, and somehow I think that, I mean, there are already several really great tools for this. One of my favorites is Moogle, which is supposed to, you can just ask it, show me a theorem which does this, and it will look through MATLib. And I have checked yesterday, it will in fact just find this pullback, um, which would have saved me a day of programming. Um, One thing that I am quite uh, interested in is there's a lot of literature for people who are just starting out with lean. I'm sure there's a natural numbers game, there's mathematics in lean. I'm sure that if you look at the lean community website, there's I think 5 different books about how to get started writing lean. What I don't see as much is somehow these is resources for somehow people who have grown just beyond uh, these basic resources. Um, in computer science, the first course you take is how to do the basic stuff. It would be going through mathematics and lean, for example. And then the rest of your degree you spend doing more advanced stuff. And somehow I would like to see some of this more advanced stuff, somehow more guides on how to do this advanced stuff. Um, for example, what I'm very curious to read is if people have thought about sort of how to do proof planning better, how to make sure that uh, what you have in your head actually translates well to a computer, how to write short, efficient proofs um, instead of these behemoths of 200 lines, which take a lot of time to compile. And so these are some of the questions that I wanted to ask the community is, does this exist? And if not, then maybe this would be a nice thing to have. Then finally, to end on a more positive note, I did learn a bunch about lean and about sort of doing this kind of stuff. First and foremost, I've gotten a lot more comfortable with lean. Once in a while, I would try and see how far I could get proving some relatively simple theorems in model theory, for example, which is what I currently work in. And after writing my thesis, after doing a bunch in Lean, I found that I could suddenly much more comfortably prove certain things that should have been pretty easy to do. One of my main takeaways was I should spend less time behind the computer when I write Lean. Somehow, the time spent actually writing down proofs seems to be much less than I expected, and I should have spent more time sketching things out on paper, thinking about how to do things. One thing that really surprised me is I did a lot of manipulation of topological spaces, and I did all of this using category theory, using formal limits and subspaces, which I mean, it worked, it compiled, but it became very messy. And so I realized that category theory in Lean is not always the answer. Of course, there are those who say that outside of Lean it is, but when formalizing, somehow this intuition betrayed me. It's I found that it's much nicer to actually work with concrete types and objects that somehow have the exact behavior that I want coded into the definition without me having to use all this machinery from category theory. And maybe most importantly for the rest of the community, I think that I'm now able to write simple proofs that can be merged into MATLib without much supervision and only minor corrections, which is something that I'm very happy with. Thank you for listening to me, and I'm happy to answer any questions that anyone might have.